when you have a data, any data, normally when you try to sort of like what we call, let's say this is, let's say I put here. Okay, let's say you have the data. Normally the data will sort of like, if you have many data, it's sort of like tabulated like this. Okay, tabulated like this, more or less like this. Okay, so this, let's say this average. So you have somehow, you have this shape like this. Okay, since this is what we call the normal distribution graph lah. So it's always normally when you do, not normally, I mean it's found every time when you try to gather some data from population in random way. Okay, you must make sure you gather the data randomly first. Okay, and then those data, more often than not, they will accumulate like this, like a bell curve. Okay, so this also we call it bell curve, or other name for this is also Gaussian curve lah. But normally people call a normal distribution. How data distribution, how data distribute. So especially when you gather, for example lah, in the real life example, when you are measuring the weight or height of something. For example, let's say if you try to measure the weight or height of all the individual in Malaysia, then you plot in the data, you will get this. Most of people will sort of like be in the center of average. Also, you can also see this data in what we call in income distribution. That's why you have if in a country in Malaysia, there are people that are very rich, there are people that are very poor, but most of the people in the middle, not so rich, not so poor. Okay, so this how you get this what we call the bell shape. Also, you can see this if let's say you are doing exam, the national exam or whatsoever. You can see this data in the what we call the exam scores and so on. So basically it's to show you that you can see this again and again in your life. So Statistic basically use this sort of like this graph. They assume, that because this is happen again and again, so when you are doing statistic in DOE, they are basically relate whatever finding that you get to this normal distribution. So that's what they do lah. So they will because your data, regardless you do experiment whatever, if you do it randomly, that's why it's important, randomized experiment. If you do randomly, you will find that your data will sort of something like this also. Okay, and as I said before, when you learn about sampling basically this is your population. Let's say this population. The sampling is basically you take some. Okay, so this is basically sampling lah. This sampling, you take some from the population. So you might say, okay, this data is fine for the population when you have a lot of stuff, a lot of things. But then what happen if let's say I run the experiment only 13 experiment only? I run experiment only 12 experiment only. Will my data will look like this bell curve also? That is where you have in statistics, they call it central limit theorem. Theorem. They said that the central limit theorem is state that the sampling distribution, the sampling, you know the sample. That's why we talk about sample and population. The sampling distribution, how data spread. Distribution will what we call the distribution of sample mean. What does it mean by sample mean? Mean is average. Mean is average. So for example, when you sample a data, normally you divide, right? You divide by number of size, so you get the average. So sampling distribution of sample mean is basically will approach normal distribution as sample size, or we call it n, bigger lah. So to get the idea here, if like this, let's say you are in your family, you measure the height, you measure tinggi you, you measure the height in your family, height. Normally your family maybe like 3, 4, 5, 6, 7 person in one family. So normally for that, you will see that the graph may be something like this lah. It's not so much variation. But the more you sample, for example, you sample, instead of your family alone, you sample also your friend family, your cousin family, you will see that the more data that you have, it will somehow will look like this also. It will reach this curve lah. And then if you go large enough, for example, all the family in the in Malaysia, you will got somehow something like this lah, normal distribution. So this is basically what we call the central limit theorem. They say that sampling distribution will approach normal distribution as the sample size sample size increase. So what have this to do with the DOE? They said that if you perform more experiment, the better, because after all, when you do the analysis, they will sort of like look on the basis of this normal distribution graph, because they assume, statistics assume, every data will look like this, will after all eventually will look like the normal distribution. So they will compare your data with the normal distribution. So the more the data that you have, the more correct the the analysis lah, more or less like that. So that's why you are advised to do a lot experiment than than the more data, the more experiment, the more data that you have lah. Okay, so you have this normal distribution. So let's say I draw here. So you have something like this, and then you have this thing. This is normal distribution. Okay, so in the middle here, one of the characteristic of this normal distribution is that the mu here, we call it mean. This is mean, mean. Okay, and then you have this deviation, the spread, we call it deviation lah. So the spread is called deviation, standard deviation. Okay, so meaning that if you have mean there, so that is mean. Let me draw something like this, and let me put this color lah. It's mean, and the standard deviation is here. That's the thing. So let's say this is in the normal distribution data, they put mu equal to 0 lah. This mu equal to 0. So this is 1 standard deviation, this is 2 standard deviation, this is 3 standard deviation. Similarly, if you go the other way around, you have this in the negative side, you have 1 standard deviation, 2 standard deviation, and then 3 standard deviation. Okay, so you have this. So you are symmetrical. So one of the properties of this, let me put down lah, so that it will not touch the thing. So this thing, okay. Properties of normal, properties here. First is symmetrical lah, symmetrical. Second, the mu equal to 0, the standard deviation, and then third, the standard deviation, the sigma equal to 1. So this is basically the properties of standard normal, we call it standard normal distribution, standardized. So that's why whatever data that you have, they will sort of like correlate with the standard normal distribution. When they correlate your data with this standard normal distribution, they can find the region of significance and so on. It turned out that what we call this thing, if you are 1 standard deviation here, if I draw here, and if I make the what we call the shade here, so if you are 1 standard deviation from the side, from the mean, 1 standard deviation from the mean, from the either side, you can see this thing have the very they cover the probability, they are covering 68%. 68% mean that of the area lah. So when you do the testing, the 68% confidence lah, more or less like that. So if you go, for example, if you do one standard deviation, so you get 68%. If you have two standard deviation, it is 95%. So that's where you got this 95 thing. And then you have three standard deviation, that is 98.7%. Okay, so this this area under the curve, okay, this 90, this thing, the 98, 95, 98, 68, 95, and 98.7, we call it the what we call the area under the curve lah. It's basically area under the curve lah, under the curve. And you know, if you have something curve, in order to get the area, what you do, you need to integrate, right? You integrate. Okay, but the function, this function itself have a very, what we call very the function, if you want to see the function, is like this: fz equal to 1 over 2 pi e, and then negative 1, 2, and then it just grows lah. I mean, the function itself is difficult to integrate lah. Okay, difficult to integrate. The idea is that. So, but because this standard normal distribution is fixed, because you see the word here, standard, meaning that it's fixed. There are people don't want to integrate this. People create a table so that they tabulate the data rather than they integrate again and again, because you can see the normal distribution, standard normal distribution, always the same. The mean is always 0. The standard deviation is always 1. So because of this, people create what we call a table. So if you look here, see here, just to show you how to read the thing. So you see this one standard deviation, okay, from the mu. So if you see the table, this is the table. You can find this table in statistic book or in any website, statistical website. You can get this for free lah. So we are looking at standard normal distribution here. Okay, standard normal distribution here. So here you have 3a. So you look at this one. You see the area there. So basically, this is the area, the probability area. So you have also this thing. Okay, so meaning that the area here from so this, if you look here, all this from negative lah, 0, and then this negative. So that's why you see everything here is negative. And then here you see positive. So that's why everything here is positive. And here is the from the 0 to z. Okay, we said before that from 0 to 1 standard deviation. Okay, we want to see what happened from 0, from here 0 here, let's say here 0 to 1 standard deviation. What is the area for that? So from the table, it's very easy lah. So you go to the table. What is the table? Standard table. Okay. So from the table here, you can see that they have Z score. You call Z. So Z is basically the horizontal lah. So the horizontal, because our Z is our sigma. So we want at this Z equal to 1. Okay. So if you go here, Z equal to 1. Okay. Z equal to 1 and then 1. So this is basically just the addition lah. So if you go here, so this is 1.01. This is 1.02. 1.02. This is 1.03. We want exactly at 1. So we take this. So if you look the value here, 0.3413. So let me put here. So Z score for when sigma Z when they are 1. So basically apa lupa dah. Wait cepat lupa ni. 0.3413. 0.3413. Whatever lah, 13. Okay, so this is basically they are region between this lah, between this. You can see here between 0 here, so between mu and here number 1. So you can see that is 0.3413. So because here you can see they are like from both sides, right? From both sides. So here, because one of the properties of the what we call of the standard deviation normal distribution is symmetrical, so whatever on the side here is also the same lah. It's also the same here. So this also the same. So you get 0.3413 times 2, you get around 68 lah. 68. 0.3413 times 2, you got 0.6826 lah. So, and if you convert into the, what you call, into the percentage, you get 68.26%. Okay, why they are 2, 6 and so on? Because remember, this is integration. Okay, integration. So actually this table, if you look this table, this number is not 4 until 4. You see here 0.3413. This just approximate. Actually they are longer. Okay, so that's why you don't get this thing. So that's why this area is sort of like more or less 68%. That's why how people get 68%. So when you got this 68%, when you dealing with the DOE later on, you normally find the probability, the confidence interval and so on. So that is where that thing come from lah. Okay, so as I said before, this is standard normal distribution. This is the ideal. We call it the ideal lah, the ideal. But when you do the experiment yourself, the data that you got, the data that you collect is not normally ideal. So what you do is that you relate. So let's say your data, you basically relate to the normal, what we call normal standard. Let's say your data, they show like normal distribution shape, normal distribution shape. So you need to correlate with the standard normal distribution lah, distribution, the one that standard lah, the one like this lah, like this. They have mu equal 0 like that. So your data, why I said it will, because as I said before, this data, whatever you got, data that you get, okay, normally it will spread out in such a way that it will be like this. Whatever data that you get, more or less, it will spread. If there is real randomization in your experiment, you will always get something like this. The average, everything, most of the thing will accumulate in the average. So when you get that sort of like shape, like a normal distribution, let's say you have this shape like this, you convert into this thing. You convert into this thing. How to convert that? Is you see something here, you can see if you see this table, you can see there are formula there. Z equal blah 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 like that. So meaning that you can see you have mu is a mean for your data, and then x is the your point of interest. The sigma here is standard deviation, how spread the data, the z, and then you get z lah. So you put your value here, the x, the mu, and the what we call this the sigma, and then you get z. So and then once you get z, you can use this table. So once you use this table, you get what? You get the area. So from there, you know whether your data is have in the region or not in the region. From there, where you know that whether your thing is significant or not, whether your hypothesis is significant or not. So that's basically the idea lah. You need to convert your data to normal, standard normal distribution. In what we call, in the handout, I give you something like this. Something like this in the handout. Okay. You have, let me put myself here. Okay. You have a certain thing, certain basic statistic. Okay. Certain basic statistic for calculation for the statistical analysis. These are the standard, the basic one lah. So you have the mean. The mean here is basically the average lah. Mean is average of data. You can see there the average of the data. So you can also have another. So this describe the data. It describe the data. Whatever this thing is describe the data. Is describe the data. Describe the data. So mean, they describe the central tendency of your data. It describe central tendency of your data. Because remember, we want to relate with the normal distribution. We said that most of the data, when you gather more enough, then you will get this normal distribution. So when you have normal distribution, the middle is important. So that's why whenever you gather the data, you want to find mean. So mean describe the central tendency of your data. Okay, and then that's everybody knows how to find the means. Another name is average lah. Average. Okay, before we go further, you look here. There are two parts: population and sample. That's why we need to learn about population and sample before, because they are different in calculation of population and sample. Population meaning that you take everything. Sample, you take part of population. So you can see there are some different later on. Okay, so we go to mean. We're done with mean, and then variance. Variance is how spread the data. So for example, let me put another ni lah, senang sikit. So this is just okay. So let me put so you have this mean. Okay, you have the data. You have the data like this. Data like this, and then you see at the middle there are a lot accumulate. So the spread here, the spread of the data here is we call it variance lah. Not variance, I mean, yeah, variance lah. Variance is not really variance. The idea of variance is this: you have this data. Let's say I draw something like this lah. Something line is much easier to understand. Okay, this is middle. Let's say no, not middle. Let's say this is a line. Let's say this is the line. And then your data, let's say I put on this line. Okay, let's say this thing. So the mean, let's say 1, 2, 3, 4, 5, 6. You have 6 data. So the mean is the middle. Is the middle of the not the middle of the position. Is the middle amount of the data lah. So this is mean or mu lah, or mu. The what we call the variance is basically how they find the variance. Variance is basically they want, this is middle, right? Let me put here middle. This thing is middle. Okay, so to calculate the variance, basically what they do is that they try to calculate from here to here, and then from here to here. Let's say I put it down. This is middle, this is mean, and then you calculate also from here to here, and then this from here to here, from here to here, and then from here to here, and then they average it. Okay, so the problem is when you do like this, you have a negative part. You have the negative part, and you have the positive part. So negative and positive will cancel out. Okay, they want to find the distance, your data, the distance of your data to the center, to the average. So they do this. They find the distance between this your data to the what we call to the center lah, to the center. To the center. Imagine this is here, 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 this is here lah. The problem, you have negative and positive. So that's why before you can find the spread is basically the average lah, the average of this distance. Before you can find the spread, you need to square. That's why you see in this data, this thing, you can see they are square. To find the variance, you need to square sum of the square and then divide by n. N is basically sample size. If you have 5, then 5 lah, divide by 5. So basically, they square this thing is basically to what? To avoid the cancellation out. So that's the reason for that. So that's why you have this. Mana tutup ni? So that's why here you basically square. We call it sum of square. Sum of square. So basically you have the data. The data, let's say the data is your x minus the middle. Middle is mu. Mu is average. You know how to find the average. So they square this thing. Because they want to find all the data, they sum everything. And then in order to sort of like standardize, they need to divide by n lah. So this is basically the what we call the formula for variance. Okay, you get the formula for variance. So is for timing is easy, right? But when you square the data, you will get these big numbers. You add the data, you square, and then you add. You get the big numbers. So that big numbers is not to the same unit of the mean, because the mean you don't square. So in order to get back to the unit, the equivalent currency we call it. So this thing, they square root lah. They square root that, and then x minus mu squared divide by n. Okay. So this is what we call the variance. This is variance. This is the standard deviation. Standard deviation. So standard deviation, you heard about standard deviation. Standard deviation is just basically the spread lah. We see before the standard deviation have the symbol sigma. So that's the spread after you square root the thing. Okay, so that's why here you can see the one here. This thing I need to bring up lah. Easy. Okay. So you can see, so this you have the variance there, and then you also have standard deviation. And we see before this thing, right? We learned before how you get this thing. If you put in the normal distribution table, you get this thing. If you look here, there are something different there. There are something here, n minus 1. This is called degree of freedom. This is called degree of freedom, or DF. Okay, you will find this in DOE. When you do DOE, you will find this DF. So that is degree of freedom. Why? What is this? Why is n minus 1? If you look here, the sample here, you know the sample, you don't calculate the entire thing. Because let's say the entire population is n. Of course, the sample will not be n. So that's why the division is not by n. You don't know, because remember, when you do this thing, when you do this part, you want your result to represent the population. Remember, the idea of doing sampling is that your result, you want to represent the population. So you minus 1 in such a way in order for it, because n minus 1, because it's not n, it's not population. Because if population, then it's n. So you minus 1. And the reason why is minus 1? Why is minus 1? Why when you see degree of freedom, why n minus 1? Kenapa kecil? Why n minus 1? N minus 1 is basically what we call it just what we call it, it just how what we call how is what we call how many piece of information. This degree of freedom, basically the definition of degree of freedom is basically how many what we call how many piece of information or value. We talk about data value. You can vary in data set. Okay, maybe it's quite abstract, so let me give the example. Let me give example n minus 1. Okay, let's say you have a 3 set of numbers. Let's say I put here lah, it's easy, I put here. Let's say you have 3 set of number. Let's say you have 3 set of numbers, and all these 3 set of numbers give the mean of 10. Okay, so you can choose any set of numbers. So for example, let's say I make it simple, 9, 10, 11. So the average is 10. So this set number 1. Let's say set number 2, I can put it 8, 10 and 12. Also will give you what we call the mu, or the average is also 10. If I go the third set, let's say I put 7, 10, and then maybe we put the farther lah. Let's say I put this even farther. Let's say I put 5, 10, 15. All these three set will give mu equal to 10, the average. Degree of freedom, meaning that this, if you pick 2 set, let's say if you pick 2 set, you can pick any numbers for these 2. You can pick any numbers for these 2. But once you pick these 2 numbers, this third numbers cannot be, you cannot simply pick anything. It's fixed. Understand or not? I mean, once you choose any 2 numbers in 3 set, you cannot vary the last one in order to get mu average of 10. For example, this, let's say number 2. If let's say you choose number this and number this, you cannot vary this thing, because you can vary this thing, but then once you choose that 8 and 12, in order to get mean of 10, you must put 10. So you don't have any degree of freedom there. You mean that you are not free there. You only have degree of freedom for 2, but you don't have degree of freedom to choose for the third numbers. So if you have this in this case, you have 3 numbers. 3 is your n. Let's say n is 3. Let's say n equal to 3. So degree of freedom, df, is basically n minus 1. So equal to 2. So that's why you can only free to choose for these 2 numbers. So that's what does it mean by degree of freedom lah. So now the question also, people might ask, why n minus 1? Why not n minus 2, n minus 3, n minus 4, whatever the thing? That's need some what I call mathematical proof lah. But the idea is this: allow the sample standard, because if you look here, the statistic here, the very idea for this is basically you want this standard deviation for the sample more or less match closely to the standard deviation of the population. So there are mathematical proof for this. They said that if you n-1, they will be closer to the standard deviation of the population. Okay, we not deal with that, but that's the idea lah. So now you understand, if you have sample size of what we call 100, so the degree of freedom is 99. Okay, so that's why n-1 lah, n-1. Remember, you don't know the population amount, the n. For example, let's say the amount of human in the amount of individual in Malaysia. Even though you do banci, I mean you try to knock every door in Malaysia, maybe you miss someone. So the n for the population, sometimes you don't know. So this n-1 is basically they said that when you try to sampling some of the population by dividing by n-1, whatever you got, the result that you got, the standard deviation that you got, or the variance that you got will be closer to the real true population numbers size lah, size. Okay, so now then we go to standard error. What is standard error? So if you look this picture, what is the picture? This picture. Okay, this picture. So you know the standard deviation. Standard deviation is basically the deviation of the data. Okay, let's say you have 5 of this. Let's say this is only one. Let's say one measurement. What we call one measurement. Let's say you have 5 of this. Let's say I put this. Let me copy lah. Let me copy this, and then Ctrl C, and then I go here. Let me go down. It's easy here. So I copy, Ctrl V, and then I make it smaller like that, and then I Ctrl C, and then I again make it smaller. And then let's say I do it again, Ctrl V, and then I make it smaller. Okay, let's say you have this thing. Okay, let's say you have these 3 measurement, A, B, and C. And then of course maybe this thing is a little bit different lah. Instead of like this, maybe the data will be something like this, a little bit more and a little bit less like that lah. So let's say this C, there are more data and so on, and you calculate all this mean and the deviation. So now if you try to find the standard deviation, okay, before that here, the standard deviation here mean what? The standard deviation meaning that if you take the average of all this thing, you get somehow something like this. You take average, you get somehow like this lah. Like this. So that is standard deviation. How spread the data in terms of value lah. So that is standard deviation. So now let's say this thing, the standard deviation here, let's say I draw like this thing is like that, and then this I put the different color. Blue is maybe like this, and then here is basically maybe like this. Okay, so that is standard deviation for the A, for the B, and then for the what you call this C. So standard error meaning that what? Meaning that standard error, you try to draw all this thing. Let's say I put the same mu. Let's say I take the average of all the mu. So let's say this average of all the mu, and then I try to put all the standard deviation for each overlap each other. Meaning that, for example, here you have from here to here, the red one. So green one maybe from here to here, and then for the blue one maybe from here to here. So similar like before, if I draw something bottom here like this, and I try to find what we call the what we call this thing, the distance and so on, and I make the what we call the average, I will get the average of the standard deviation. Okay, so I will got the average at the end of the day. I will got here something, the average for all these 3 thing, this thing. So this is what I call standard the standard error. This is standard error. It's basically the spread of the standard deviation, okay, is a spread of standard deviation of many sample. This thing, when you do this thing, when you find the spread here, this is sigma. This is basically the spread due to the data lah. But this is the spread due to the standard deviation itself. You combine all the standard deviation, and so that's what we call the standard error lah. Standard error. So if you look here, this thing. So we look here. If you got okay, so the one that I show you is basically this. The one that I show you just now, when I take all the standard deviation and then I line in the line, the number line, and then I find the average for that, you get this thing lah. So if let's say the population is known, let's say the small population, the class 1, let's say you want to see the score, the student score in the exam, you have class A, class B, class C. Let's say this is class A, class B, class C. Let's say this is student. Let's say this is the one that I show here is basically the student score. Let's say this is basically student score. So basically when you do this thing, you are having A is one population, B is one population, C is one population. Because let's say you are interested on this thing, you don't want to make this 3 measurement to represent the entire population. You just want to deal with this small population. Let's say you believe this is one population, meaning that you have 3 class A, class B, and class 3. Class A, class B, and class C. For example, let's say you are a teacher or you are lecturer. You are teaching only 3 class. So that 3 class is only your what we call your population. But let's say you want to estimate, okay, you want to estimate towards the population. Let's say in the school, let's say in the university or school, you have like 1,000, let's say you have like 50 or 60 or 70 plus class. Okay, you are just focus on this thing, the 3 class. If let's say you want to sort of like measure, you want to if you do this analysis using this sample part, what do you mean? What do you do is basically you want your result to represent the population. For example, if here, let's say when you do all the thing, you get the mean, let's say 70 out of 100, meaning that 70 in terms of marks lah. So when you do this and you want to reflect to the population, you said that I got 70 in mean, so meaning that the mean for the population also must be close to that. So that's what you do when you do sampling. But let's say you are, this is the only thing that you are interested. You don't interested but to project your data to the whole population. Then this is your population, class A, class B, class C. So that's the only population. You have 3 population only. But if you want to project your data to the whole, the big picture, then you need to use a different formula. The different formula, if as you see before, is just basically you minus 1 like that lah, minus 1. And here you can see they are dividing. So you can see standard error. Okay, standard error is basically the standard deviation. The standard deviation divide by this n, square root of n. So n is sample size. The n is sample size. N is sample size. So this, why you divide by n is basically this sort of like the phenomenon that if let's say you have the class like this, let's say you have 3 class, and then this population, the whole population. So if let's say you, what we call, the more you take the sample, let's say you take lot of more sample than 3, let's say this you take 3 sample, this you take more than 3, let's say 12 sample. So then the more you take the sample, the less new info you need anymore. That's why you divide by square root of n. What does it mean is that because this 12, let's say the total population is 20. Let's say the total population is 20. If you take 3 sample out of 20, then there are more data that you don't know. But if you take 12, then there are less data that is needed in order for your result to close to the population, because the number itself is already high. So that's why you divide by square root n like that. So that's have something to do with this phenomenon. The idea is this: the larger your sample size, the larger the n, the lower your standard error. Okay, the larger the sample, this what we call the n, the lower the standard error. Of course because if your n is nearing the population, if your n here, whatever, if your sample n is nearing the population n, then the error will be less because when you calculate the whole population, you are confident 100%. But if you do sampling, the more data you do, the more is closer to the whole population And then you have the confidence interval here. Okay, they have something to do with what we call with the confidence level. Before we learn about confidence level, the 95, the 75, the 99 point whatever that thing. So that percentage is a confidence level. So you need to differentiate between confidence level and confidence interval. Confidence interval here is the value. For example, if you look here, they are x. This is a mean for the sample. If you look here, x is the mean for the sample here, mean, average. So confidence interval is just the value interval. Confidence level is the probability. Okay. To give the example is this Let me go to here. Give some example here. Okay, let's say you have what we call you have this. Let's say you have like before. This is population, and this is your class A, class B, and class C. Let's say class A, you have a few students. Let's say you have for example, let's say you take 4 class Let's say this is you have like 20 students, you have 30 students, you have 50 students, and then maybe one you have 15 students. Okay, let's say you have this class, and this is the whole population. So this class A, class B, class C, and class D. So now the total of this is basically 20 plus 30 plus 15 plus 60. The n sample will be 115. So degree of freedom n minus 1 will become 114. So that's one thing. So the mean, let's say you want to analyze the score, the exam score. You know the exam score is from 0 to 100, right? From 0 to 100. Let's say you take all the sample and then you found the average mean for all the sample is 70%. 70% in terms of mark Okay. So the confidence level is different. Confidence level and confidence interval is two different things. Because confidence level is something like 95%, 99%, and so on This you decide. Confidence level, normally you decide how much confidence you want. You see, you remember the power calculation. Confidence interval is basically the what we call the value of the mean, plus minus something. For example, here, if the average of all the class is 70%, so this is basically your mean your mean. So you plus minus, let's say you have this standard error, something like that. So let's say you have this what we call, let's say here 75%, and then this is what we call 65%. So this is what we call so you can say your thing is 70, 75. So you basically your confidence interval is basically 70 plus minus 5 So let's say this is 95%, 95% confidence level, okay. So let's say this is 95% confidence level. What does it mean by this? 95% of confidence level for the confidence interval between 70 and 65. So let me put here because this is everything. So what does it mean here? How to interpret this is basically you say that you are 95% sure. You are 95% sure that what we call that the score of the population will lie between 65 to 75. So that's what does it mean, because what you do now is you're sampling. If you look at this statistic here, this thing, if you look here, there are no confidence interval for the population. Because why? Because if you manage to what we call to measure everyone, to ask everybody, so then you are 100% confidence lah. So that's why there are no confidence interval for the population. You know for exact, for sure, this is the thing. This is the average of all the what we call all the score, because you calculate all the sample size. But for the sample, you cannot do that because you don't know what is the n. Because if you see the sample here, if you look here, you take 4 sample out of many other possible class. Maybe you want to project your let's say this is the exam score. You give the same exam to all other students in one let's say in Malaysia. So you are confident that 90% of times you sure that the score of the population will lie between 65 and 75. So that's what does it mean lah. So if let's say you increase the, normally when you increase the confidence level, for example you have 99% confidence level CL, this thing is also increased lah. For example, your mu is 70, so this is 90, normally 90, this is 80. So you can see the higher your confidence level, the bigger your confidence interval, because that is what we call, that is intuitive lah. Because if let's say you take this range from 60 and 80, is much more, you more confident to say that the value that you will get from the population, the other person will fall between 60 and 80, because you have like a bigger interval. So that's why you are more confidence. So the more confidence that you have, the more bigger the interval lah. Okay, so that's what does it mean by confidence intervals lah. So this confidence interval is depend on the sample size and variation lah. Sample size and variation. So I think we have to, because it's now 4:52. I will focus just a few things only. Let's see the statistic part. Okay. Here. Okay. So here, if you look this confidence interval, they have something to do with the T. And this is what we call the T-test, T-score, whatever. Whenever you do the DOE, they are, sometimes they call it student T-test, whatever. So this is the T. The T here is come from this thing, the what we call the normal distribution. If you look here, the Z score and this thing is more or less the same, but something a little bit different lah. Because I think I will not continue further, because it's already 4:53. It's better for me if let's say I let you to study a little bit about this statistic, and then maybe tomorrow we will discuss further lah. So I think I will stop here. I will stop until confidence interval, because the reason why this part is needed is because later on when you do DOE, you understand what you do. If not, you just putting the value in the DOE software and you get the value and then you don't understand. You just, okay, you don't know whether it is right or wrong and so on. So you just put the value. So that's why some statistic is needed. Even though the what we call the discussion is quite what we call dry, this thing, calculation and whatever, is somehow is needed during the DOE, because DOE after all is the statistical analysis. You need to at least understand the basic of that.